My name is Harry Ricker. This is the Cosmology discussion group meeting for Sunday, and I think what was March 26th. Is that right? No, 23. March 23, 2025. And everybody's welcome. Okay, it's nice and sunny here today. Jim Keene, I see you're here. Jim didn't finish talking yesterday. He got cut off. So I've invited him back to complete his discussion. He has also said that he's going to answer some of the questions that were raised by Vladimir last Sunday. And so he's going to just address the questions. So Jim, I'm going to turn it over to you.
Okay, let me, I'm just trying to get this little window out of the way here.
Again, let me just comment a little bit before we start. I've had my vision isn't as great as it used to be, so a lot of these slides are a little small for me to read. If you go to the view on the right-hand side, there's a says view. You can click on that, and then at the bottom there's full screen. So
I'm sharing full screen now.
Yes, I noticed that when you started up. Okay.
Yeah, per your suggestion previously, I'm going full screen right now.
Okay, I could. It's a little better. This slide is pretty busy. There's a lot of stuff on it.
Well, actually, the origin of this slide was just meant to be a summary of the equations in the original paper, binary mechanics postulates. And then I added the text in red, which made it even more busy, just to sort of guide the discussion in a presentation such as this. But yeah, there's a lot in the slide. It's a summary slide, but please just focus on what the discussion is at the moment. Where we left off was the strong bit operation. And I have
now here's where I have a problem. I have no idea what that means.
Okay, well, that's one of the 4-bit operations that changes the system state over time, and it involves transfer of quanta, or a one state, within spots. And the illustration I like to show, which may help clarify this idea, is here, this illustration. And I'm seeing, how do I get this thing off the screen? Oh, okay, great. The strong bit operation is shown in the upper part. At time equals 0, we can have a one state quanta shown by the black arrow here. And what can happen at time equals 1 is we're shifting now from the spot unit in the X dimension to the spot unit here in the Y dimension at time equals 1. And so that's what the strong bit operation does. It's cycling bits within spots. And remember, a spot corresponds to an elementary particle as reckoned in binary mechanics. So that all of this happens within a spot, and it's a way to connect the what's going on in one dimension with what's going on in other dimensions. Remember the first 3-bit operations that we discussed, the unconditional, scalar, and vector, were all in one dimension. In other words, nothing left a dimension to go to another of the XYZ dimensions. In this case, though, we're talking about interdimension transfer, in this case from the source spot unit in the X dimension in this illustration to the Y spot unit. at time equals 1. Now, the strong bit operation has a very sexy feature, very interesting, and you might say weird feature, that it is disabled by inertia. And inertia, forget any other definition of inertia you have in mind. I'm going to define it my own way right here. Inertia P is the product or and function of the two states of the MNL loci within the spot unit, and that can equal 0 or 1. Now notice that here we have in the x dimension at time equals 0, inertia equals 0 because we have 1 times 0 is 0. So inertia is 0. And when that is true, then at time equals 1, this x to y spot unit quanta transfer can occur. Now, the neat thing here is that what if this quantity I'm calling inertia, and forgive me because I know inertia is used in many different ways in physics, but just forget the word if you want. It doesn't matter. What is important is the equation for inertia that I presented here in the upper left of the slide. If inertia equals 1, this means at the bottom left diagram here that both quanta m and l are in the 1 state at time equals 0. Notice that at time equals 1 in the lower right of this illustration, both nothing has happened. There was no transfer. So in other words, the strong bit operation is the transfer from one XYZ dimension to another, but it is blocked if inertia exists. In other words, the interesting thing here is that if the inertia equals 0, as we see in the upper left diagram at t equals 0, what is this empty circle? Well, it's an M-type locus, but it's actually a neutrino quanta. It's a locus in the 0 state. And so here we're seeing that the neutrino is required for this strong bit operation to occur. Again, to summarize, if P equals 1, the black circle and the black arrow shown here, the L quanta does not move from the X spot unit to the Y spot unit. And in the next unconditional bit operation, here's the point to focus on, ladies and gentlemen, it shifts out to the next spot. In other words, not shown here, but in the next application of the unconditional operation, this one state quanta will shift into the red spot here, which is in fact a quark spot. And matter is conserved because this is an electron spot, and the dark red spot here is a right-handed d quark or down quark, which is in the matter category also. So matter is reserved, matter and antimatter are preserved in this transfer. Now, when that occurs, we have in fact defined the mechanism, the fundamental mechanism for all motion. Okay? Now, you don't get that in Newtonian mechanics. They just say stuff moves. Forget how it moves. We're just going to block out any curiosity as to what the mechanism of motion is. We're just going to try to describe it, velocity, acceleration, et cetera, but forget about any mechanistic view of what is actually occurring. So the strong bit operation in this analysis has given us a big payday. That payday is the revealing the mechanism for all particle motion. So when we look out in our world and in our universe, we see things moving. This, I believe, is what is going on. Now let's go back here to our terrible crowded slide. Now this equation 16, I'm not going to spend much time on it. It has to do with the chirality of space and that we have left-handed and right-handed spots. And it's just defining this locus must be empty. And that's our subscript D, can either equal N or P for the next or the previous spot unit within the spot. And that has to do with the chirality of space. And so that's what equation 16 has to do with. And I don't think it matters much to spend much time on that here. Now, the final payday is the bit operations order. When we apply these 4 bit operations, we have a system state at time equals 0, shown in the lower right in our final equation 17. And we can then apply these bit operations in a certain order. This is important because when in work that I've done, it became obvious very early that different order of application of these bit operations give you different results. Mathematically, the outdated quantum mechanics people would call this lack of commutation of the operators that do not commute. In other words, they don't give the same result depending upon the order that you apply those operators. So here we've gone from bit operators in quantum mechanics to bit operations to quantize everything in binary mechanics. And so the operator order that I think is probably correct is a scalar, unconditional, vector, which is our magnetic one, and then the non-bold F, which stands for our strong force when that's true. And that when you apply them in that order, you get a new state of the universe, which is our bit function at time equals 4, assuming that these 4 applications occur in an equal amount of time, so that we're 4 ticks later in the world with this bit operations order. Notice that since the operations do not commute, which is a similar thing in old-fashioned quantum mechanics and in binary mechanics, they don't commute. It means what? It means that only one order could possibly be physically correct. Because we have one universe, don't we? So that only one of these orders could be correct. Right now, we think the SUVF order shown in the lower right here is the correct order.
Okay, Jim, there's no equation 17 on this slide.
Oh, you can't see it? It's at the bottom here.
Okay.
Do you see it at the bottom?
No.
But 17, it says bit operations order.
No, it's not on there. Okay, so
maybe I should go
off.
out of full screen and go back to the way I was doing it before, because we
No, I can see it for one.
You can? I see.
Yes.
I don't see an equation 17.
I do.
Under strong bit operation?
I do it too.
No, under bit operations order, it's at the very bottom of the slide.
I don't see it. All right.
Well, ENC sees it.
I don't know why I don't see it.
And Vladimir sees it, I think.
Yes,
I see it. I see equation 17.
I think I know why here.
Oh.
I've got the videos at the top and they should be at the side. I'm not sure how to get them.
Just pull them over, I think.
All right, now I see it. All right.
Okay, let's move right along, gentlemen. Let's see here. I can use my arrows. This is working great. Okay, now in this slide, we're going to just to provide some context, cross-reference the conventional force classification here at the top in pink with the 4-bit operations defined in binary mechanics that we just walked through last week, and now we're continuing this week. The electromagnetic one, which is thought to be mediated by photons, maps to 2-bit operations, the scalar or electrostatic bit operation and the vector or magnetic bit operation. So there you have that. The strong bit operation, thought to be mediated by gluons, which keep the quarks inside a proton or nucleon inside there and not wandering around all over the place. This strong force in conventional views maps to the strong force in binary mechanics. But this can be confusing, I will admit, because there can be a danger using the same word in the conventional force classification and in the binary mechanics bit operations. That word is strong. So all I can say there is apologies if that causes confusion, but forget the word strong. It's the equations that matter. The equations define what's going on. Now, this gray box here gives us talks about the so-called conventional force of the weak and neutral weak forces with the W plus and minus and the Z bosons. And they map to the unconditional bit operation, which in binary mechanics is not a force. The unconditional bit operation produces these particle interactions. These bosons, W and Z, are identified as related to right-handed matter d quarks in, if you look at the data that the people talking about this weak and neutral weak force actually present. Now, oftentimes the data presented is more important than the theories or ideas of the investigators. Oftentimes, outstanding experimentalists are lousy theoreticians. Let me just say that. I don't want to offend anybody, but I think that's a fairly true statement in many, many cases. In this case, if you look at their data, what they're calling W and Z bosons really seem to relate more to the right-handed matter d quarks in binary mechanics. Lastly, we have gravity, which I have a question mark here what the particle is. They want to invent one, say the graviton or some other particle, which, by the way, hasn't really been observed and I don't think will ever be observed. Gravity in binary mechanics maps to all 4 of the bit operations. In other words, these bit operations produce gravitational phenomena. And so that in binary mechanics, gravity is a derivative, not primary force. Thus, quantum gravitation unification is achieved. Now, if we transition this down arrow here from legacy physics to 21st century physics, we have this summary table below. And the point I wanted to mention is first, several points. One is that the unconditional bit operation is not a force. And so that's why we have what I call the weak force boondoggle up above, that it's a complete mess. It's phenomena that they're investigating and measuring, in fact, are not forces. And even a Nobel Prize was given for this discovery of the weak force. And now they have to go back and say, gee whiz, it's not a force at all. At any rate, that we have our unconditional, which does not have the properties of the 3 forces defined in binary mechanics, which are quite simple. That falls into a very nice, neat pattern. There are 3 components: a source, 1-state bit or location, which we saw in each of the 3 forces, an adjacent location, which has the potential for that force, and a 0-state destination location for each of the three. Now, in binary mechanics, if you want to discover and define a new force, you have to add a new line to this table. So that sort of concludes the slides for the binary mechanics equations. And I'm trying to, gee whiz, go to the other ones.
All right. So now you're going to change topics, correct?
Yeah, to talk about
All
how
right.
we got the primary constants.
All right. That was the issue raised by Vladimir. Okay.
Exactly.
Okay. Before we do this, I have a number of comments and anybody have any questions about the previous discussion before we move to this discussion? Okay, no takers on that. I have some comments. One is, let's go back to that slide.
Okay, let's see. I'm going to have to go back and change. Okay, which slide?
The one behind this. So
the one,
the next,
this one?
no, the one where you talked about the different forces.
Oh, yes, this one.
That one. Okay, so this is the essence of everything that you're doing, in my opinion. Okay.
Yeah, it's a summary slide.
But this slide here, I mean, this slide, you've essentially solved the unification problem of gravity and quantum mechanics, but it doesn't really, but you've got it, you talk about that at the end when you got a question mark. And to me, that seems to me, this is the holy grail of physics today, to be able to unify gravity and quantum mechanics. And you just kind of like, oh, it's basically at the end of your force classification table, and you mentioned that at the end. Seems to me that's kind of like the big headline of your whole presentation.
Well, one can make that headline, definitely. What we're talking about, though, is with outdated quantum mechanics, that is sort of in the excluded or rejected category, as well as space-time curvature in general relativity is also in the rejected category. So it's sort of weird, you know, like people want to combine two wrongs and hope to get a right, and they're going to call it quantum gravitation unification. So that's my editorial comment.
All right. Well, here's another. I mean, you've got these big conclusions and big things that you're doing, but you're they're just like, it's kind of like the whole gravity unification issue, which is the whole, the holy grail of modern physics, the theory of everything, the holy grail that they keep talking about. I see a lot of videos on YouTube where they talk about this, Sabina Hassenfelder and all these people, and yet you don't really make this a big, seems to me each one of these topics here, electromagnetic, strong, weak, neutral, weak, gravity, each one of these deserves its own discussion, which may be one or two, maybe more slides in each of the categories.
Well, yeah, if you want to go back and talk about the history of where everyone got things wrong. But why do that? Why not just move forward and break new ground? And that's what we have over here. And so this slide just simply cross-tabulates the various efforts which are now prevalent in YouTube videos, as you mentioned, with what's going on in binary mechanics.
All right, what do these X's mean? This means that it's true, or that
Well, that it maps to the unconditional force, so that the weak force
what does the arrow next to the X mean?
that it is produced by the unconditional.
Okay, so that's another comment I would make is you got symbols on it. You see, you got a bunch of arrow X, arrow X, arrow X under gravity. You don't.
Yeah,
So,
the
so there
gravitational
needs.
effects are produced by all of the actions of the 4-bit operations.
Okay. Well, my
And
point
I've
is,
actually done computer simulations showing that, in fact, we get gravity-like effects from uh, uh, the action of these bit operations. And so the whole idea that gravity is something sort of a separate thing is really just you know, an outmoded way to look at things. Also, what people don't do
all
in
right,
today's
Jim. Before
world.
you proceed on with your, why isn't there an arrow X on these other symbols here? Like there's under electromagnetic photon that's just XX, but there's
Well,
a arrow symbol.
it's just trying to cross tabulate and map the conventional ideas to where you're going to find them in binary mechanics, I guess.
All right. This is kind of problematical in my mind. So you need something. I think you need more slides, and I think you need an explanation of what these symbols mean that you're using, which I've criticized before because going back to the previous slide again. Here's another one down here. You got 1 minus Li. I don't. Li is apparently an operation on the bit L.
One minus Li is not Li. In other words,
No,
the
you don't
destination
understand
is.
what I'm. You don't understand what I'm saying. I don't know what Mi and Li actually mean. I don't know what bit. What is a strong BS? That means the strong bit, and is that what the S
That's
means?
the source one state location. Source.
Okay, so these you need some kind of a legend or something that tells us what all these symbols mean. There's a BD down here. I don't know what BD means.
Well, there is a legend in small print here in the slide. Actually, this
You
is a
didn't really talk
summary
about.
slide.
Hold on, Jim. So you should have talked about these what these symbols mean. You should have talked about that before you presented this slide.
Well, that's what the entire binary mechanics equations talk is. It explains exactly what all these symbols are.
Yeah, okay, but they're very unfamiliar and kind of difficult to understand. So my point is I see this as something that would help people to understand what you're talking about other than making it just seem like a lot of mysterious symbols on a slide. Do you understand what I'm trying to say? I mean,
Yep.
I looking at this, I don't really and then you got an arrow transition from legacy physics. This slide could be broken up into a series of slides that would be, in my opinion, easier to understand. Anyway, that's my comment.
We need people to, in fact, write entire books on binary mechanics. So
I realize that.
I
But we
invite
need
you.
to understand what you're talking about here, and I'm having a hard time.
I agree with you, Harry. It's very difficult to understand for me too. And what is important, using these classical notions in your binary mechanics, I don't understand it. You named step, one bit, it's okay. For quantum mechanics, it's okay. And I agree with your approach for quantum mechanics. And what is important, even your table, all your ideas, going to quantum mechanics only. You're talking about these particles, you're talking about, I don't like the word force, It's not right because what does it mean force? Force, it's a classical notion. In quantum mechanics, there are no forces, there are interactions only. There is a strong interaction, there is weak interaction, whatever it is, but there is no force. That's why to put forces, it's not the right word. The next one, you put some space, time, this classical physics into your model. I cannot get it. For quantum mechanics, you need only, by the way, in quantum mechanics, there are no space, there is no time, there is nothing from classical physics. It must be. That's why your approach as a quantum mechanics approach, I'm ready to discuss with you, no doubts about it, but don't name all these classical notions inside of your binary mechanics. The most important is gravity. Gravity is a classical notion. That's why gravity force between particles, nobody took a look without you. And I don't understand how it works even in your approach. And what is important, I don't like it because there is between elementary particles, there are no gravity. There is none. Gravity, it's classical notions. It's
Well, glad
something
you have a lot of
outside of
company.
your approach.
You are not alone. You have a lot of company. There's a lot of people who don't understand what full quantization is all about. And so that, like you're not alone. You have many companions in that.
Okay, but Jim, what I'm trying to say is, and I think what Vladimir makes a good point, is this could be expanded. And first off, this here is kind of confusing because you're in essence taking the existing standard model physics. This is my understanding of what you're doing. And standard, and the way they're talking about things now, they say there are five forces. I mean, I counted them. One, two, three. You have the five forces, and I agree with Vladimir that that's kind of not really correct, but that's kind of what they talk about, five forces. So but they're really interactions.
Guys, it's a wrong word. Don't use it. Force, interaction. What is important, Harry, you're absolutely right. It's a quantum physics. Jim, you use only what they have. Quark, neutrino, and all this stuff. You're saturating, the existent already notions in quantum physics with your approach. I like it. I like it. It's good, because let me tell you, standard quantum mechanics based on supposed on Schrodinger equation, it's absolutely wrong. Why? Because in quantum physics, there are no space, time, gravitation, all these classical notions, they are emergent. There is some field, quantum fields, it's absolutely wrong field, it's a quantum notion. That's why you look, use in your theory. I do like it, as approach to quantum physics. But take the notions like step, bit, qubit, whatever you're doing, put some special notions of yours without any connection to the classical notions because they don't work in this way. And gravitation, nobody to talk without you before, I mean, in quantum physics. And you are pretending right now that you found gravitation inside of your model, in your theory. It's a very strong statement, and then you continue,
Thank you.
oh, at
Thank you.
last, quantum gravitation.
I
I don't like
appreciate
even
that.
this combination. 1 second, Jim. I don't like even quantum gravitation notion because quantum is a quantum and gravitation is a classical physics ensemble of quantums. That's why, please continue as a branch of quantum physics, saturating your movements with the existing notions of quantum physics, and don't tell about the gravity force because there are no forces. It's a classical notion. There are some interactions, and I don't understand gravitational force or gravitation interaction between particles. Nobody before you done it, and I don't know how you did it.
That's a good point. Okay,
Well, you've got a lot of company there, and so that at least you have a lot of comrades with you in that bucket.
okay. So to follow up on what I think Vladimir is saying, I am only, the more you talk on these slides, the more I listen to you talk, I get like a small increase in understanding. Okay. And
Well, that's good. That's progress.
right. And the more I get a little bit of increase in understanding, the more I think, yeah, this sounds good. But the difficulty is that to grasp the fundamental concepts and what's going on turns out to be pretty difficult. And what I'm trying to say is, and I think Vladimir is trying to say, is that the concepts are more important than the equations. That would be my point. In other words, you talk about equations and bit operations and moving around in spots, and that sounds good, but I don't really understand what the concepts behind it really are, what it is you're trying to show or demonstrate. And that's why I think you need more slides, and you need to, connect the ideas better. You've got 17 equations. That's a lot of material there. And
well, just in the last few days, I published 2 new papers on binary mechanics, no space in there, .blogspot.com, both on the equations and on the derivation of the primary and secondary constants. So that that's the effort that I'm doing. Yes, we need people who are better graphic artists than I am. We need people who can write prose better, perhaps, than I can. And so that we're looking forward to those who want to break, slides up into many different slides or so forth, to go forth and to do that, and to report back, and I'll interview you. Give me what your results are, and I would be happy to have you as a guest and interview you.
All right. Okay. Any other comments here? And I think we'll take up the next topic in the next session. Dan, I haven't heard from you. Do you have any comments?
Well, I suppose I could have a lot of comments, but I'm really all ears at the moment. Yeah, it is quite a complex in the way it's described by Jim, and that's because these concepts are somewhat new. They're a distillation of some ideas with which we are familiar from, classical physics and maybe more modern ideas as well. To be frank, I'm not convinced that, let's be a bit blunt now, if you forgive me. I'm not convinced there's any truth to this. I mean, it may work. It may be a model which provides constants, or is consistent with experimental results. But it doesn't. It's not an intuitive. Well, I've got a prejudice. I'm basically a classical physicist. I mean, Vladimir talks about classical physics. I'm fundamentally a classical physicist. I'm actually Newtonian, So and a lot of Jim's ideas fly in the face of Newtonian dynamics. So consequently, I'm not really ad idem with this, but I'm endeavoring to listen and to learn more about it. So I've so many questions really that it would absorb too much time, but I want to listen, and I will come in as necessary.
All right. See you in. Okay, I've started the recording. Okay, welcome back to the second part. I was hoping that Bob French would be here. I don't see Bob French. Bob French knows more about quantum mechanics. I have to sort of say that my knowledge of quantum mechanics is extremely thin. And, um, you know, I sort of was hoping that he could give us some comments from his point of view, which is more of a quantum mechanics point of view, rather than a classical physics point of view.
I might mention one more thing, if I may, Harry.
Go ahead.
Yeah. I think we referred very briefly last week to this, and I've been in correspondence with Jim just over the last week about it. I mentioned, the proportionality constant, say K in E equals K MC squared, not necessarily being unity. And I think I might have said it was 4/3. Well, I think actually it was 3/4 in the analysis of Hassenhurl, which is actually before Einstein, a year or two. It might have been 1904. He actually published, sort of like E equals 3/4 MC squared, or you should the mass which would be attributable to the energy would be 4/3E. Well, I've done some work on this, looking at the analogy of, say, sound waves in air. And if you look at Rayleigh's theory of sound, he looks at a dissipation in air, say, which is dependent upon things like the dynamic viscosity of the fluid and the density and so on. And you get this factor 4/3 coming in. So, on the basis of classical theoretical physics, I've sort of carried this over into electromagnetism. That's a bit of a first. But Jim, it's also come out, if I understand, in the wash from Jim's ideas, because he's looking at these cubes and these particles and these bit loci and so on, and he's getting the difference. I think he adverted to this last week, the difference between the number of sides of a cube as distinct from the vertices, and hey presto, this factor of 3/4 or 4/3 comes in. So I just thought I'd let you know it's the progress we've made over the last week. We've just exchanged some information, and I've exchanged some a paper with Jim, and he's explained a little more his ideas. So there you are. I've been rather critical a moment ago, but perhaps from two disparate approaches, there is some similarity in at least one respect.
Okay. I don't have any more comments other than stuff that I could say at the end. So maybe let's let Jim proceed to his second topic, and then we'll have more questions and discussion later.
Let me do one more comment. Comment is,
he's
talking about steps.
Hold on.
And
yes, we hear
Can
you.
you hear me?
Yes, we hear you. Vadimir's talking.
It seems that
Right.
I'm going to have to restart my computer because the whole screen has gone screwy. So I'm going to restart and get right back to you. Okay.
All right. I see that the screen is blank.
Yeah, right.
Okay. All right.
It's all messed up. I just have to restart my computer. It must have
All
been
right.
a
We'll just
cosmic
continue
ray.
to talk here while you're gone. All right, Vladimir, while
yes,
Jim's gone.
I want to make the most important comment for me. I'm not an expert in quantum physics at all. It's all a university, that's it. That's why, but I have a prejudice against quantum mechanics because they use some derivatives, meters, seconds, and all this stuff. It doesn't work for me at all because I'm a classical physics like Iran, and I don't want to put these notions, classical notions, inside of the quantum mechanics. What is the most important? In his talk, sometimes Jim, for me, talking about the right notions. Step one, step two, step three. At moment T0, T1, T2, T3, I don't like it because there is no continuously running T, there is no space, there is nothing. It's a quantum physics. As I told you, quantum physics, all the 100 years ago, it was classical physicists. They had done some good job based on the classical knowledge, classical notions, and that's it. But it's time right now to cut it. Many times I told you that my friend Felix Lev, he done this quantum physics based on operators. I don't like it. I don't like on these beats. I don't like any approach avoiding all these classical notions. That's why I don't like this, talk about this model, electric, magnetic, gravity, and all this stuff. It's all the classical notions. It's time already to cut them, to forget about them, and to talk T0, T1, T2, 3. It's exactly according to his steps. And for him, it's steps. That's it. It's a contemporary, it's a personal computers. I don't like it very much. I'm not familiar with something more deep in this approach. But what I do, always I'm trying to understand the main ideas of people, what they're doing. And the main idea to go with quantum mechanics without any classical notions, it will be fine for me, because this is the only one way to do quantum. It is mathematical quantum physics. There are no physics inside of it, as for me, because classical physics, even comparing with experiments, how do you know that you measured something for one particle? Why are you talking about the size of proton? I have no idea. What does it mean size for you guys? And you're talking about 10 to the minus. I don't know. That's why, the main approach to avoid all these classical notions, I do like it very much. But this is the only way to go with mechanics. How good, how bad, I don't know. Gravity, I am absolutely wrong with it. I cannot see gravity inside of particles. As many times I told, particles, they have only four momentum. That's it. That's it. No gravitation, nothing. And even this interaction he introduced, they are falling from where? From standard quantum physics. Then I want to ask you, what is the difference between you and quantum physicists right now? Because you use the same notions, but you're doing different mathematics or different computer calculations. Up to you. Okay, go. You see what I mean? There are no new notions. And to pretend that it's a theory of everything, I'm absolutely disagree with these even words. Quantum gravity. Quantum is quantum, gravity is gravity. It's a two different story. Many times I told one object or ensemble of objects. That's it, simple like this. That's why. And you are trying to combine one object with ensemble of objects. It's
All
a
right.
very
Let,
good.
let me ask you this, Vladimir. I didn't see you yesterday in Rogers.
I was yesterday, believe me, but I couldn't go with this, our, meetings to the green room. I cannot do it. I saw it.
Okay.
If you want to talk about
All right.
yesterday,
My comment that I wanted to make here was that that's what he was talking about is that there's this approach that uh, that attempts to be unified field theory. That's another one of these things of attempting to create a theory of everything or a unified theory, unified physics, and it doesn't really get quantum mechanics in it, as far as I could see. And then you have the other approach, which is the people who have adopted the standard model, which is based on quantum mechanics. They're trying to create a unified field theory or a theory of everything based on their approach to quantum mechanics. So we have it from two different directions, but it doesn't seem to fit together really. And I think that's what you're trying to say. And you seem to be saying, from what I gather, that the notions can't really be transferred between one and the other. And that's what you're.
it's exactly my point. Even the notion field means immediately for me ensembles. You don't have field for one particle. You don't. Even this approach, I like it, mathematical approach, but it's a classical physics. There is electromagnetic field, immediately ensemble, and all this stuff. Why even quantized field? I don't understand it. What does it mean? Field, it's a classical notion. It's ensemble. And let me remind you, all the time, this double split experiment. You're looking for one object, you lost your wavelengths. You don't looking on each object, you have your wave, you have your pattern, you have your interference. It's a very good point. Why? One experiment, it's quantum physics, another one classical physics. And difference between them, one object or many objects at once. Simple as it. That's why, all these attempts to combine quantum physics with gravity, it's absolutely wrong. It's a bullshit. Even with notions, it's absolutely wrong. That's why they're trying to develop some mathematics, something how to explain it and all this stuff. But they're trying to combine bird in sky and fish in the water. It's a different story. There is such a story by Krylov in our Russian, books. You cannot combine them. It's absolutely impossible. And even, Richard Feynman, in my papers I put, it's impossible to explain in a reasonable way why photons or wavelengths behave in such a way. He was he was a very smart guy. He knew everything about quantum physics and so on and so on. And nevertheless, based on his knowledge, much better than mine, he couldn't understand this and explain this experiment. Only I understand. I explained it very simple. One object, many objects. One object, many times I told you, we have our molecules around us. They have kinetic energy. Fine with them. But temperature is not kinetic energy. It's an average kinetic energy for the whole ensemble of them. Only then you can introduce this classical notion, temperature, volume, pressure, all these classical, force, all these classical notions is based on experiments with ensembles of particles. That's why when we're talking in quantum physics, we measured some number up to the 13 digits after the comma accuracy. I don't believe it. It's the only mentioned with mathematics only. They're trying to find some number that will be close enough to the result of experiment. But I don't believe in the result of the experiment, because how are you doing, guys? Your experiments with one quantum object. I have no clue. I have no clue. That's why, all these, combinations, quantum gravity is gravity, quantum is quantum. Don't combine even these two words together. I'm crying about it all my time, guys. And this is a very good example, Jim theory. I'm not so much understanding even what he's doing, but I like his idea. Okay, let's stop all this, space, time, and all this stuff. I have one step, I have temperature, have time, 0, 1, 2, 3. You have some quantum steps. I have the first step, the second step, and so on and so on. And don't name all this electromagnetic and all this stuff. What does it mean for them? And then to tell me, in my approach, this is explanation of quark, explanation of electron. This is something else. And combine your approach to the standard notions of quantum physics, but tell guys, you done these equations from Schrodinger equation. It doesn't work. In my standard right now, personal computer standard, I have the same approach, and look at this. This is one particle, this is another, this is the third one, and so on and so on. That's why, guys, all my life, the last year, I'm talking to you more than 1 year. Jan, I started, by the way, 1 year ago with you. Remember my 8 presentations.
Of course.
And I started to cry. Guys, I'm a classical physicist. Please don't touch it. You're a classical physicist, you told today. Sure.
Yes,
sure,
and I'm becoming more so as time goes on.
Yes, and I hope it will influence, my influence will be on you too, guys. That classical physics, it's one story.
Oops.
He's frozen.
Yeah, I've noticed that was happening, and I wasn't really sure what was causing it. Now he's frozen. Okay, I'm surprised that Jim hasn't gotten back yet. Um, I'm not sure what's going on. Yes.
But Vladimir mentioned in his absence, the propensity to use the word quantum, and to tag it on to other things like gravity and so on. And it's something I noticed as well. I mean, everything is quantum and quanta, like a quantum computer. I mean, what's that? It's really a very powerful computer, and perhaps these units can simultaneously have zeros and ones, or maybe something in between. So they call
it's got qubits.
yeah,
Instead of
qubit.
zeros and ones, it's got qubits.
Yeah. So the
Whatever
Q,
a
it's a,
qubit is.
but I mean, it's a fancy name, quantum. Once something appears Q, and I mean Planck's ideas, which introduced this, that you wouldn't have a continuous transmission of energy, and it would be in discrete quanta. Well, that was basically very, very specific, to the transference of energy in black body radiation, and it was really an hypothesis, which he said would, whether it was really true or not, he doubted it himself. I think it was just so it's extended to everything now.
Right. Well, what Vladimir said, I thought was kind of interesting was when he talked about field as a classical notion. The first thing that occurred to me was this idea of quantum field theory. What does that mean? Quantum field theory. And I've never understood what that means. What is that string together of words?
Or quantum electrodynamics is another one, I suppose.
Right, quantum electrodynamics. There you go. That's another one. I've never understood. I got these books on quantum electrodynamics and tried to read them and couldn't make any heads or tails out of what it is. So what I think Vladimir is saying is that what you have a completely different types of physical notions in quantum mechanics and classical physics, and then to bring them together in some way is just creates contradictions. That's my simplistic view of what I think he's trying to say. You have to redefine. You have separate types of notions in quantum mechanics and different notions in classical physics, and you can't really bring them together, and that's really where the problem is. That's my interpretation of what he's saying, and I think they're battling over whose set of notions, whether your quantum physics notions or classical physics notions, are going to be the superior notions. Right now, the quantum people are winning, I think.
And that's the distinction between relativistic physics and pre-relativistic physics. I mean, sometimes relativistic physics is considered classical, but in my definition, I'm talking about pre-special relativity and pre-quantum mechanics. That sort of classical physics which existed beforehand, and I think it has a distinct way of looking at things. It's I don't know. Various terms could be used, like realist or even naturalistic, as distinct from these other areas, not only quantum physics, but also relativistic physics, which introduce these paradoxes, which on the face of it appear to fly in the face of Greek logic. Common sense.
Yeah, okay, so I see that we got Jim's presentation back. Okay, so to let you know what happened was that Vladimir was talking and then he disappeared. And I don't think I've seen him come back yet, so I'm not sure what's going on, but I do see your slide.
Okay, well, should I just go ahead and dive in here?
Right, unless we have any more comments that people want to make before you start.
Well, before the huge cosmic ray zapped my computer 5-10 minutes ago, there was a lot of discussion about gravity and general relativity. and also quantum mechanics, actually, binary mechanics sort of rejects both of those. And my own study of lunar laser ranging has excluded general relativity already. So what I find is that people are many people are reluctant, simply ignore the fact that a theory has been excluded and just waltz on merrily talking about general relativity or whatever, as if that exclusion event had not occurred. And so I think Ian would generally agree with me that a lot of people just simply ignore data that excludes the theory and just pretend that we don't care. We'll talk about all the so-called predictions of the theory and forget that it's been excluded.
Okay, I have a comment on that. That seems to be so now we're talking about the philosophy of dissident physics. And one of the issues that I have is, and I noticed that Ian hasn't commented on this, but we have this discussion about Ivor Katz's theory. And what happens in the discussion is that people say, why are you messing with physics? It's perfectly fine the way it is. And there's no need for your theory at all. And so therefore, everything that you say, we just going to reject because we can go look on the internet and find an excuse that somebody has written up that explains things satisfactory to us. Do you quite understand what I'm saying? In other words,
yes,
people want to hold on to the old concepts, and in the case of Ivor Cat in the discussion that we've been having, there's an experiment called the Wakefield experiment, which he explains perfectly well according to his theory. And David Hume absolutely cognitively refuses to accept the explanation, which is correct. Okay, so what you have is you have a guy who says, I refuse to accept that this explanation is correct, although it is correct within the theory that's being used to explain it. And he just says that's wrong. Now, the point is you have to, when you're presenting binary mechanics, you've got that roadblock in front of you. In other words, people who don't want to accept change, they're perfectly happy with the existing ideas and they don't want any new ideas. And somehow you have to get over that barrier.
Well, I think that my main strategy, but I'm open to suggestions, is that merit in the end is important. And so eventually ideas that don't have merit will fall by the wayside, and those with merit will rise to the top of the pile.
Right. That's kind of the traditional view of it. The point I'm making is that a lot of the effort, and you've commented on this before, it's about communicating what your ideas are. And a lot of people will just not even pay attention, and the question of whether or not you have merit in your ideas or your theory doesn't even come up because your theory never gets to anybody's attention because they won't publish it in any journals. And then the other thing, which is the deadly sin of all, it will be labeled fringe science.
Well, I think I mentioned before this battle, that you've expressed that we have against established views, and the way they can either just ignore evidence or maybe attack us. But I also considered that within the dissident community, people who individually don't agree with the mainstream ideas are fighting vociferously against each other as well. Now, I hope I'm not sort of a prima donna, but when I see the sort of long discussions about the Wakefield, which is interesting, and David Tillman, all the rest, I mean, it becomes very personal and impolite and attacking people and calling people idiots and all this sort of stuff. I think I quoted these two Latin scholars, about 100 years ago, two Irish Latin scholars, and they both had unimpeachable nationalist principles, which was basically becoming quite acceptable at the time. But one includes the other of being a castle spy, which is the worst. The worst insult you could give to an Irish nationalist, a castle spy over the use of the word cum with the subjunctive in Latin. So give you an idea like that. And I also quoted Benjamin Franklin, in this respect, that it might be no harm if we dissidents did consider that we must hang together, or most assuredly we shall all hang separately. We're our own worst enemies. We're fighting and fighting and fighting, and we're correctly criticizing the mainstream for having closed minds and not addressing the points we raise objectively. But to be quite honest, I don't think we are bereft of that criticism as well ourselves. We have our own dissident theories, and when we come across another one, we oppose it, and sometimes we oppose it in harsh terms. Now, I'm very skeptical about accepting anything, so I've expressed my doubts about Jim's ideas, although I've also expressed the strengths of them. But I certainly hope I'm always doing it in a polite way. And perhaps there's some evidence of that in that I have been criticized for being overly polite when I'm hosting one of these Saturday meetings. Like when I have a speaker talking, whether I agree with him or not, I'll gently maybe raise concerns, but it's my function not to attack him, to give him every credence and politeness and so on. People say it appears that the NPA is officially sanctioning some way out theories given on our Saturday presentations. But the question is really to be open-minded, and I'm sufficiently old-fashioned to say polite as well. Yes, don't become ad hominem in attacking the man rather than the message.
Okay, Jim, I think the point of the discussion is that it's kind of incumbent on the presenter to try to make his ideas clear and understandable. But then there are people, as I pointed out in my little story, who, no matter how clear you try to do it, they just refuse to accept it. And I guess you have to move beyond that point. But so let's see how you do with your second topic, and maybe we can help you make it a little clearer if it's not clear.
Fine, wonderful, thank you. Okay, let me see if I can get back on track after having the disaster of my computer completely go berserk.
Yeah, I do want to warn you that I think we only got about 10 minutes or so.
Okay, well, we can, continue as you desire. Okay,
I'll warn you when the interruption is going to occur.
The first slide here is showing sort of like a game map that you might have in various computer games, where we have different areas here. The dreaded wasteland area here, in my opinion, is where the assumption of continuous variables for energy, space, and time, and the theory that space and time are continuous and even curved and so forth, reside. And in this area, there's a lot of woe and consternation and difficulty. So if we have our hero—
All right, Jim, let me stop you right here. Okay, so going on our theme about making the ideas clear. Why did you pick three things: energy, space, time? Why are those your three things? Some
Well,
people would say,
maybe
why not mass? Why not? Yesterday we had a discussion where the primary fifth, the fifth dimension, taking space and time as four dimensions, the fifth dimension was said to be mass. You're adding in energy. Why are you doing that?
well, the basic thought is that we wanted to go full quantization of energy, space, and time, and we can represent energy in kilograms. The space would be in units of length or meters, and time in seconds. And it so happens that these three values map to the fundamental units of measurement in physics.
Okay, now let me stop you there. I saw a video a couple of days ago where they were talking about the SI units, the fundamental constants of measurement systems. And there's more of them there than energy, space, and time. I think they have, you know what I'm talking about, the SI
Oh
units?
yeah, like for example, charge.
Right. Okay, so the question comes up, why have you reduced those fundamentals, charge and all these other ones? I forget, there's charge, current, I forget all of them. There's
Well,
luminosity.
as you're going to see in my presentation as it rolls along, Harry, actually charge is energy meters, just like
Okay, I understand
Planck's
that. So you
constant
need, hold
is
on.
energy. Go
Okay,
ahead.
hold on. But you've essentially, here's my point. You've essentially chosen these three things, which that's basically postulates on your part, correct?
Yes, full quantization is the name of the postulates, and there's three of them. For one for energy, one for space, and one for time. And it's quite interesting that some of these other quantities like Q, charge, is actually has the units. And this you're never going to see, at least I never saw it until I worked it out. But I'm sure other people are aware of it too. Charge has the units of joules meters, just like Planck's constant has the units joules seconds. There's a parallel there. And so, but with parsimony and the desire for Occam's razor to be effective, full quantization, all it needs is these three parameters, and everything else flows from that.
Okay,
And
so
so
your first,
if you need a fourth parameter, let me know, because
okay,
I'm
hold on,
unaware of a need for any other.
hold on. Okay, so from
Yeah,
your point of view, you're going to construct you're constructing the physical primary, your primary physical constants, or your primary physical uh, parameters that you're using are three: energy, space, and time. And those are presented as axioms and postulates. So they're your starting point. You made this assumption, and now you're going to construct your theory based on that.
correct. Well said.
Okay. So if I want to question why you chose those three, that's not really, they're chosen because that's what you chose to do as postulate. Okay. So now we can move on. Dispense with that.
And they're the basic units of measurement in science, which is something which we can't ignore. So that
Yes,
great
but they're a
minds.
subset. They're a subset of the bigger SI units.
But yeah, I mean,
Yeah,
is
but
that quite true? Mass or energy, length, and time are independent of each other. Yes, they need special measures. But if you're talking about things like electricity, you need another value. It cannot be expressed in terms of these three. It either has to be current or charge. ampere or coulomb. They're independent. You seem to imply that you could derive charge in terms of these, of energy.
Yeah, I have that on a slide, Ian. This is an excellent point. You would think by listening to a lot of talk, physics talk, that charge was something different than, and not accounted for by these three primary constants. But in fact, charge, as I'm going to show you as we move along here in the slides, has the units of joules meters. Just
that's action. Okay, well, let's see that. That's the same as action. Yeah.
No. Action is joules seconds.
Oh, I beg your pardon. Yes, okay.
So that we have a certain symmetry there. So that, in fact, people have talked about charge as if it's something different than, but really the three primary constants can express charge totally and completely.
Well, I'd be interested in seeing that, certainly.
Okay, well, let's move along then. Let's see what the next slide shows. So anyway, we have our first task or quest is to reverse engineer the secondary constants, which are unexplained measurements wrongly called fundamental constants used as input parameters in models like the standard model.
Let me stop you here. Okay, so you need to clearly, so your primary constants are energy, space, and time, and then you're going to talk about secondary constants, which you're not really clear what you mean by that.
I mean the fundamental constants in physics textbooks in Appendix A.
Okay, so you've started with these three fundamentals, and then from those three fundamentals, you're going to explain what the physics books call as fundamental constants, but you're calling them secondary constants. Is that correct?
That's correct.
Okay.
Now, with full quantization of energy, length, and time, the obvious next question is, what are the values for these three quantized items? And so that the up arrow here is we're going to have to dip into this region of our game map here, the land of the wrongly named fundamental constants, and see if we can reverse engineer these what I call secondary constants below to obtain the primary constants above. This was precisely Vladimir's question. Where do these three numbers come from?
Okay, we got less than 2 minutes.
Can I ask what electron EDM is supposed to mean, please?
Electric dipole moment. It's a measure of the like a water molecule has a positive electric dipole moment because it has more positive charge on one side compared to the other.
Okay.
Okay.
Thank you. Cheers.
So
right, we got about a minute.
Okay. On slide 2 here, we have the incomplete flawed physical theories, which name Appendix A and call them fundamental constants. And here are the values. With multi-millions in research funding, the scientists appear very authoritative. On the other hand, binary mechanics alleges that this is the greatest body of unexplained observation in physics, or at least one of them, and is these so-called fundamental constants. So our Appendix A in your standard textbooks should be titled Most Important Unexplained Data in Physics.
All right, we got less than a minute. This, in my opinion here, this is where a lot of people are going to really get their backs up. A lot of physicists would say, how dare he suggest any such thing?
Well, that's good. I'm happy to hear that. That's good news.
Well, okay. Okay, but you're gonna get cut off here if you start up. Okay, so Jerry here now.
Hello. I overslept actually.
Okay. All right. So now we're going to get Jim's. Still not seeing it, Jim.
Can you see the,
All right. There we go. All right. Let's go back to the previous slide that you went through pretty. No, that's not it. The one with the guy with the glasses, the sunglasses. There you go. Okay. All right. So we have two sections here. Sold by obedient physicists as fundamental inputs required by incomplete, flawed physical theories. Now, my appendix A, what's the bottom one? Is that any different? Are they the same parameters there?
yeah, the same parameters, but the label is corrected to most important
Oh,
unexplained
I
data
see.
in physics.
Okay, so what you're saying is that your opinion differs from the opinion of the obedient physicists.
Exactly.
Yeah, instead of
This is
mainstream,
all
he is
introductory material. You know, this is just to get you into the actual topic, which is to derive the primary constants and how that was
right.
done.
Okay, now, but
So this
here's
is just
an issue.
introduction.
Here's an issue. I mean, for a lot of people, this is what really this is the basis of what physics is. I mean, for people who believe this, I mean, they believe that these fundamental constants are the fundamentals of physics. And am I wrong in this?
Yeah, I think you're right. That's what this slide is all about. I wrote a whole paper called Fundamental Physics Constants Doctrine. It's a
Right.
doctrine.
So, Ian, I want to get kind of Ian's point of view on this. This is what you did for a living, isn't it, Ian?
Oh, you mean in the standards area, Harry?
Yes.
Well, yes and no. Although I was more concerned with writing specifications than actually measuring these values. We did have a metrology laboratory, but yeah. So, um, yeah. Well. Therefore, I suppose Jim's ideas are uh, a bit foreign to my way of thinking. But I have to try to be open-minded and maybe amenable to revision. Uh, Certainly at present, I'm not convinced that these are explained because they are. I mean, Jim has to give us more information, and presume in the next 20 minutes he'll do that. But as to how these are not fundamental physics constants, my basis would be taking them as fundamental physics constants.
Well, again, this is just introductory material. The meat is yet to follow.
Jim, what I'm trying to say, and the reason I'm bringing this is a big hurdle because you have this belief, this really hard belief that these things are fundamental constants, and you're calling them secondary constants.
Well, those people will be left out of the game, won't they?
All right. Well,
Like I don't understand what the problem is. You want everybody in the game? That ain't the world. That ain't the way it works.
all right. But what I'm saying is
they're voluntarily excluding themselves from physics.
Okay, but it's a hard sell. That's my point. Okay. It's a real hard sell. Okay. You got to really sell this good.
Okay, right. Measured values of so-called fundamental constants are not independent. They contain redundant information. Therefore, the equation shown here for alpha coupling constant, the Bohr magneton, and vacuum permittivity all show that there are interrelationships among these constants, and they also show something more. They show that not only are these constants not fundamental, that they could not be fundamental because of these interrelationships that exist. Fundamental values would be like my primary constants, which are independent of each other. In other words, you can't determine the value of one of them based upon the values of any of the other two. And that's what mathematical independence means, so that we get now to construct in our green area the physical constants derivation tree. And we're going to then use this to, well, we can right off the bat look at the elemental or fractional charge C, to speak to Ian's point, which is an expression for energy, mass times the velocity squared, length. So the units of elementary charge is joules meters. Just as in the elemental action, we again have an expression for energy, mass times the velocity squared.
All right, hold on. As I understand it, you're saying that elemental charge is really energy. Joules meters is
No,
energy.
I did not say that. I said it's the product of energy times length, or joules meters. That's what people tend to do. They seem to just want to fiddle around with the units and ignore what the units of these values
Okay, so I'm confused. I've confused joules.
Well, if you want to call it energy, you definitely are confused, because what this states is an expression for energy times length. So the units are joules meters for charge.
But if you substitute that into Coulomb's law, you will not get a balance for the force.
Well, we do that in this presentation, so I should just move right along, I guess. So now, what are the guidelines for the of how we can use the unexplained measurements to discover the primary constant values? The first guideline, this is what Vlad was asking. What, how do we get these primary constant values? And so I've listed 4 guidelines here. Dimension analysis. In the derivation tree, units that I just showed you, units of derived values must follow from the units of the input values. Let's see how we're doing there. Okay, the units for bit velocity V are derived from length divided by time. That's an easy one. Vacuum light speed is bit velocity divided by pi. The units for Planck's constant, h, which comes from what I call elemental action A, is energy, an expression of mass times velocity squared, time, or joules seconds. And here we have for elemental or fractional charge, which gives us multiplied times 3, our elementary electric charge E. Again, it's joules meters right here. So what's our second?
Hold on. Oh, hold on. Let's go back. I'm completely stunned by the fact that you say vacuum light speed equals C equals V divided by pi. What the heck? I mean,
well, we'll get to that. That's another guideline, and that's on the agenda.
All right, I understand that, but you got to warn people about this. I think these should be separate slides for all these. There's too much on here, but anyway, go on.
Well, this is the physical constants derivation tree. I suppose it could be broken down into 20 different slides if one wanted to. And I invite those of you who are interested to do so.
Well, I think that needs to be done.
Show us your results. Another case where, again, dimensional analysis plays a role, which is our first guideline, is electron mass. Our work with determining the composition of the fundamental particles in binary mechanics showed that there are 3 quanta in the rest mass for an electron. And so therefore, this constant here must be, if units are to be, dimensional analysis is to be followed, must be 1/3 of the rest mass of the electron. So our first guideline was dimensional analysis. The second guideline that I've listed here is theoretical constraints. Binary mechanics postulates imply specific limits and or constraints on possible values. Let's see where that might come into play. We just wanted to talk about the vacuum speed of light. Well, the fact is that a quanta cannot move in any arbitrary direction in binary mechanics given the spatial model of a lattice of spot cubes. So therefore, the question is that that bit velocity must be, this is a theoretical constraint, bit velocity must be greater than vacuum light speed. So now the only question is how much greater? And I chose the value of pi, which in fact, well, you see, with the fact that quanta can only move in one of 6 directions in and out of a spot cube in our spatial cubic matrix of space, how does a quanta in a light signal get from any arbitrary point of a source to some other arbitrary point in space as a destination? And it turns out that the whole set of possible paths that the, obviously it can't take a straight path because it has to go, it only has 6 possible directions it can enter or exit a spot cube. So therefore these paths must be longer than the bird, as the crow flies path. And we chose the value pi because that represents the average path length of the entire possible set of paths that a quanta could take to arrive at any arbitrary destination from a source destination. So that's a theoretical constraint there. That's an example of a theoretical constraint. What else do we have here?
That could be 2 or 3 slides in your presentation. That's a lot of information right there.
Yeah, well, thank you. I consider that to be a compliment. Okay, there may be some more theoretical constraints. Yesterday, I just released a paper, this whole presentation in the version of a paper on my website. And so that those who want details that I may leave out here, those are there in that paper. A third constraint or guideline used to discover the primary constant values was basic formulas in Physics 101 books applied where applicable. In the case of Planck's constant, we're talking about spin in the proton and electron bit cycles that I've talked about on other occasions. And we know from classical basic physics textbooks that one can sum the individual parts of a spinning object, their individual angular momentum, sum them up, and to get the total angular momentum of that object. Let's say we have a bicycle wheel that's spinning, and we can take each little part of that bicycle wheel and determine what its angular momentum is and sum that up to get the total angular momentum. So that's one of our guidelines, was to use basic formulas in physics where applicable. Lastly, the calculated values of the secondary constants must agree with the unexplained observed measurements for vacuum light speed, for electric charge, for Planck's constant, for alpha, and so forth. Okay, now what we have here is we've sort of completed deriving our physical constants from the primary constants from the data in all of this bevy of unexplained measurements wrongly called fundamental constants. Now we want to go in the reverse direction with the primary constants and use those to calculate the unexplained observed values, which in a way will verify. It's like checking our work. Everything must agree. So let's do that. Let's check our work. First, the fine structure constant derivation was a whole paper which can be read. And in fact, the fine structure constant is defined very simply in binary mechanics as we have the M-type quanta which are accelerated by either a scalar potential, electrostatic, or a vector magnetic potential. So these events, the number of these events divided by the number of eligible quanta to be accelerated is alpha. It's that simple. And so this gives you a tremendous victory in binary mechanics, where Feynman and other wonderful thinkers have talked about the mystery of alpha and how no one can figure it out. Well, it's really about this simple. It's a simple proportion of how many of eligible M-type quanta eligible for acceleration are in fact accelerated. That is about 0.007. And we see in this slide that this alpha value does vary a little bit with quanta density in a volume. The red arrow points to the accepted value, which we see now is not really constant, is according to binary mechanics, of 0.00729 approximately here. Next, intrinsic proton spin derivation. This is where we get a derivation of Planck's constant h by looking at spin. Here is the proton bit cycle, which we've seen before, and it contains 42 locations. And so there are really 2 to the 42 states possible, since each location here, each little circle is a location or a locus, where it can either be 0 or 1. And so that gives us the entire spectrum of hadron particles in particle physics. Light speed derivation. We can shoot, the binary mechanics lab simulator has guns on each side of the cubic volume which is being simulated. And so we have a right gun and a left gun, and we can shoot a light signal into our volume and then wait and see and count the quanta that arrive at sensors on the other side of the volume. And this gives us a curve that sort of looks like a wave, doesn't it? I remember Cornelius saying, you can't get waves unless you have attractive forces. Well, the binary mechanics equations that I presented to you only have repulsive forces, particularly the scalar force is repulsive for like sign charges, and yet, lo and behold, we have a wave, don't we? Anyway, when we do this experiment, it's a unidirectional light speed measurement, and the front velocity turns out to be, see, do I have it here? Calculated the speed with light speed equal to bit velocity divided by pi. We can measure light velocity and express it in bit velocity units of 1 over pi. Finally, in these bit velocity units, the front light velocity was approximately 0.319, or within about 0.3% of 1 over pi in bit velocity units. Now, this is a totally remarkable result. You're not going to find this kind of material anywhere else in the world of physics today, in my opinion. Elementary charge derivation. Well, we can define the elementary electric charge and so forth and calculate it. Basically, what we have here is a case where if we have 2 like sign charges at time equals 0, adjacent to each other in what I call concurrent spot unit pair here, and then let's say this charge is accelerated to the L locus position in its spot unit, we can compare two distances. One is in L units, the original distance, which is one primary constant L value, and this hypotenuse, which is the square root of 2, because this is again 1 and 1 squared gives you a hypotenuse of square root of 2. So square root of 2 minus 1 gives you a way to determine the force involved and therefore to compute the charge. Electron intrinsic magnetic moment derivation. The Bohr magneton was found to be equal to this weird value here down at the bottom in Joule Tesla. Now, an important point here, a very important point, is that if you want to insist on avoiding full quantization, in other words, you want to stick with continuous space-time, what happens at very microscopic scales, such as what I'm showing to you in these illustrations, you get huge errors, so that conventional physicists view the electron magnetic moment to be about twice the Bohr magneton value. And they spend a great deal of time fretting over this. And so here we have an example of the fact that if you stay in continuous space-time and try to do calculations at a very, very microscopic level, you're going to have the possibility, it's not guaranteed, but the possibility of huge errors, which then lead to a total mess and complete theoretical confusion in the world of physics. So what else do we have here? Zero electron electric dipole moment. This again is the distribution of electric charge in the electron symmetrical and giving you therefore a zero electric EDM, electron EDM, or not. Here we see the electron bit cycle where quanta can revolve around in the electron spot, which is a lot simpler than the proton bit cycle I showed you a few moments ago. And we see that it's quite obvious that there is a symmetry in charge distribution. You can't say the circles represent the M-type quanta, which have a charge attribute. And you can see that they're all equidistant from the center. There's no particular imbalance there. And so other labs, what I call the outsourced labs, which are our outsourced labs are at MIT, Harvard, the best universities in the UK, so that we have a lot of investigators confirming our results. And we just outsource those studies, and they agree that the electron EDM is zero. It's not significantly different than zero. And they use their old-fashioned ideas, and they say, well, this must mean that the shape of the electron is a circle. That's their old-fashioned ideas. In binary mechanics, we see that the shape of the electron is more like a spinning top. The gray circle here in the middle is the axis of rotation, and these items are spinning around that central axis of rotation. And I think we're getting near the end here. Non-zero proton electron electric dipole moment. For you connoisseurs of particle physics, a non-zero proton electron electric dipole moment has grave consequences for particle physics theories. In other words, it destroys some of the things that we call, shown down here at the bottom, P and T symmetry. And these are very important issues, which of course is okay because their whole theoretical basis is obsolete. because we've quantized things in binary mechanics. We've replaced quantum mechanics with binary mechanics. And so let's look at the electron charge positions in what I was calling at the time the central baryon bit cycle, which is our proton bit cycle. And we can see, if we look at two sort of X-ray vision views, where positive charge is dark red and less positive charge is pink, and the negative charges are yellow, we can clearly see from these two angles in the XY plane and the YZ plane that there is a charge imbalance, which is makes their theories crumble down. But as we've discussed previously, although data like this, which is agrees with what our major labs, at Caltech, MIT, Harvard, and all of the U.S. national labs, outsource a lot of work to them, and they are, basically providing data supporting binary mechanics virtually on a weekly basis. We get something new. Like the latest one is you can look up Long-Ju, that's Long space Ju, an investigator at MIT who has confirmed the binary mechanics mechanism of particle motion by showing fractional charge change or motion in a material science sort of research that he's done at MIT. And so we basically have a lot of labs that are just doing work for us, as it were, in this whole game. And let's see, so we're back to the first slide, our gameplay field here, where we have reverse engineered the secondary constants to obtain our primary constants above. And then we reversed direction and said, well, let's check our work and calculate the unexplained observed values, which we've done in all of these cases here, down below. So the unexplained measurements now account for, I can't read it because there's a defect on my screen, for all the secondary constants, and the primary constants win the game of physics. And I believe that's the end. Yes, a blank slide. That's the end. Thank you for your attention. You're very kind and patient people. Thank you.
Okay, well, I guess that means it's time to ask questions.
Yeah.
Or say something. You kind of lost me towards about 2/3 of the way through. And
Roger has a question. He had his hand up.
Right. Sorry, yeah. So, if you protested about people looking at things from a mainstream point of view, and you're discarding quantum mechanics and relativity and so forth, but unfortunately, what you're saying, I'm still looking at it from a mainstream physics point of view, and you're saying things like alpha is a variable when it's really supposed to be a constant, and you're coming up with this thing about the
What's a variable, Roger?
alpha.
Alpha.
Yeah.
Yeah, it does seem to depend upon energy density in the environment.
Yeah,
Yes.
but the mainstream is saying it is a constant. So you seem to be coming up with all these things. I don't know where that graph you had came from for that. And
that was from the Binary Mechanics Lab simulator, which is a free download.
Well, that's not supposed to be what they're getting for alpha. And so you're just coming up with all these things about like wave velocity and your way of dealing with it. And mainstream have got their way of dealing with wave velocity. And you don't seem to be connecting with anything that mainstream is saying. You're saying things which are contrary to what mainstream says, and so it just seems to be.
So in other words, you're stating that the mainstream is in a very bad situation. That's the top area here. The wasteland.
Well, that is your.
So that's where your mainstream is, in this wasteland up above on our game board.
That's your point of view, that the mainstream is wrong, but from a perspective, having had a physics mainstream education, what you're saying seems to be no connection. It's disconnect. You're just saying things where there's no connection with what we've been educated to believe about physics. So it's a complete disconnect. You're just saying things, and it's sort of like, well, how can you say that? It's just a complete disconnect.
Well, the
You're not
failures of the old theories like general relativity and
yeah,
quantum mechanics, those failures up here in the wasteland
yeah, but that they are
motivate someone to try an alternative.
yeah, but
An alternative is the hypothesis of full quantization.
but the mainstream
There's no but there, Roger.
there is
is
a
no
but. There is a but.
but. Okay, what's the but?
From the mainstream point of view, they do recognise that there are problems in relativity and quantum physics, namely how to combine them, and they do try to come up with ideas of how to combine them, like trying to have extra dimensions, but they don't agree on how to cause the correction. But you're coming along and just saying things which are just contrary to what they so far are supposed to have established about things like alpha and wave velocity, and you're not showing at all why mainstream have got those things wrong. It's just a total disconnect.
Well, it's in the I wing through those papers and slides very
Yeah.
very fast, but there are detailed papers which I had a slide for each one, and those give in detail the whole rationale and approach that was employed.
Yeah, but you haven't in this presentation. You're just presenting things, and it's just a total disconnect. So sorry about that. Thank you.
Well, don't be sorry. That's a wonderful review. I appreciate that.
I don't.
When you move from the wasteland and in the orange area at the top into the area of full quantization, it is a disconnect.
Yeah, but I
These
don't.
are two entirely different areas of the game board.
I'm sorry. I don't see why you've seen that's a compliment, because really it's sort of like we don't see how you're connected to mainstream. From my point of view, I look at mainstream.
You don't want to be connected to the mainstream.
From my point,
why are you assuming that anyone would want to be connected to a whole 100 years or more of failure in quantum mechanics and in general and special relativity?
Yeah.
Why anyone would want to be connected with that?
Well, from my point of view, I look at what mainstream says and I criticize it, and the next step would be to propose a sort of amendment to what mainstream is doing. But from your point of view, you're just going to discard everything that mainstream's done, and it's sort of like, well, the reason
Well,
for
we don't discard everything.
well,
People agree that there are three basic units of measurement in science, physics, and that we haven't discarded.
Yeah.
And so all we're saying is, what if those were quantized? What if?
Well,
so
then,
what have we got to lose? If
we're going by
mainstream,
if we're going by mainstream, which you don't want to do, in quantum mechanics, you're talking about probability. You're talking about things like Heisenberg uncertainty. You're talking about things like force vacuum and loads of other things like quantum entanglement. And there's sort of like nothing you're saying is connecting in any way with what they've built up. I mean, what parts of the mainstream are we discarding to replace it by what you're saying? It's just
that would be a good paper to write.
Sorry?
It seems to me that you would have the background to write that paper. I would look forward with great interest to what this transition entails in your view, because certainly we're not throwing away basic ideas of science. These are the units of measurement in physics that have been used classically for centuries.
Yeah, but they're dealt with now from a quantum probabilistic point of view, and my main focus has really been on criticizing the
Well,
mainstream.
that's a defect.
Well, so,
If only if you can only give a probability, you're sort of like in not as good a situation as if you can give an exact result.
well, it's the whole thing about the Schrodinger cat and the wave function and all that thing. You start off with a continuous wave function, and somehow the observation causes that wave function to collapse, and you've got a definite state of one thing or the other. And so you've got the mystery within quantum physics, and in another aspect, the mysteries of relativity. And
Yeah,
you
so
just,
that if you like mysteries and you like confusion, you
yeah,
like contradictions, you like paradoxes,
yeah,
like dualities,
yeah,
you like miracles,
yeah,
just stay in the wasteland.
yeah.
Jim, um, we got 3 minutes.
Great.
My question would be, do you have are you talking about 5 dimensions here? Space 3 dimensions, time 4 dimensions, and energy 5 dimensions. So do we have a 5 dimensional space?
No, it's three. I use 3 dimensions. That's all we need. X, Y, and Z. That's in the equations that I presented previously. And
You don't get what I'm asking. So you're not advocate as Roger pointed out yesterday. They spent a lot of time on these adding dimensions to space. You know,
right, binary
Einstein.
mechanics has no need to do that.
Okay, so that's an important point that you need to make somewhere here.
Well, I thought I made it, but if not, we've made it right now.
But getting back to this charge business, you know, where you say it can be expressed in terms of those, if you take the first Gaussian expression, um, you know, say if Coulomb's law, you'd have force is equal to the product of the two charges divided by the distance between them. There's no permittivity in there. Now, if you do that, you get things like the unit of capacitance would be length. And if you do that, you get the unit of charge would be the square root of energy times distance. I think you didn't have the square root in there. But
Well, if that's true, there's an error in my chart, and I wish that you would like point that out. I guess you think you've pointed it out right now, but is in my reckoning, the values in my constants derivation tree are correct.
Okay, Jim, we got 1 minute left. I want to just wrap it up here and thank everybody for coming by. And I think we still have some issues here to talk about, and I guess we can have email conversations about that. I see what Ian's kind of getting at, and that's an interesting point that probably, you know, I could see all of these issues. You could have like 1 or 2 slides to discuss all these fine points, which I think is kind of, you've sort of compacted everything down to you're telling us this the minimum, and then people have a lot of questions about what your minimum is.
Well, in each of these papers I'm showing now, here's one. Here's another.
All right, we got 10 seconds.
Here's another.
Or so.
All the detail is there in both text form and a number of detailed illustrations. So what we did today was take a quick tour through all of these publications. And if there's interest, one can go to these particular publications